Hey everyone, and welcome to this explainer. If you're the kind of focused learner who just loves dissecting the hidden structures of our universe, well, we've got a fascinating question to explore today. Think about this for a second. Is the spacing of the planets just the result of chaotic, random collisions over billions of years? Or is there an underlying mathematical architecture holding the whole shebang together? Today, we're diving into a concept called the universal rule of seven, or K7 theory. It's essentially a mathematical mapping of our solar system. So let's just jump right in and see exactly how these numbers line up. Our source material for this explainer comes from a massive research paper by independent researcher Gautam. Now, historically, astronomers have absolutely tried to find a geometric progression for planetary distances. But honestly, those older models usually just fell apart the second we discovered Neptune and realized how complex the Kuiper Belt really is. Pal's K7 theory takes a totally different route. He actually draws on his background in high-energy physics, specifically looking at quark-gluon plasmas in the early universe, and hypothesizes that the solar system basically functions as a massive harmonic resonator. So, just like subatomic particles occupy very specific, discrete energy levels, this theory proposes that celestial bodies sit at discrete harmonic points within the sun's gravitational field. So, the crucial point is how this theory actually establishes its baseline. Every mathematical blueprint needs a fundamental constant, right? Well, in K7 theory, that constant is derived right from the inner edge of our solar system. The framework takes the mean distance from the center of the sun to the center of Mercury, which is our innermost stable planet, and it divides that distance by 7. Now, you might be wondering, why divide by 7? The theory leans into this mysterious fundamental vibrational frequency, a rule of 7, that it suggests literally governed how mass was distributed back in the early protoplanetary disk. And when you actually do that division, you get this exact number, roughly 0.0553 astronomical units. This right here is the K unit. Honestly, you can think of this number as the main protagonist of our story today. According to the research, this isn't just some arbitrary slice of space. No, it is the fundamental quantum of distance in our solar system. It's the spatial increment, the core building block that essentially defines the potential locations for every single stable orbit in our stellar neighborhood. Once we've got that K unit, the mathematical framework gets remarkably straightforward. Actually, it's beautifully simple. The primary equation is just d equals n times k, meaning the theoretical distance of any planet is just a specific harmonic integer, what the researcher calls a harmonic point, multiplied by our new fundamental constant. It's this incredibly elegant, almost digitized view of planetary orbits. But of course, the real test for any mathematical blueprint is how well it actually matches up with reality. When we look at the terrestrial planets, the mapping is undeniably striking. Venus and Earth slide right into harmonic nodes 13 and 18, and they do it with over 99.5% accuracy compared to actual NASA observations. Mars dips just a tiny bit to 98.4%, but the paper attributes that to the intense gravitational tugs coming from the massive outer solar system, especially since Mars is sitting right on the edge of that influence. But man, the overall correlation across all these inner planets is just incredibly tight. And this actually highlights a really brilliant solution to a visual problem in astronomy. See, if you plot these planetary distances on a standard linear scale, it just looks like a clustered mess that spikes wildly right after Mars. But Paul insists on using a logarithmic scale. Think about how we perceive sound frequencies on a logarithmic scale in acoustics. When you apply that exact same visual logic to the solar system, it reveals this perfectly elegant, expanding proportional wave. Using a logarithmic graph totally shifts our perspective from looking at just physical closeness to observing pure mathematical symmetry. Let's keep moving outward and see how this builds when we leave that terrestrial zone. The model identifies what it calls great jumps, and the very first major one happens right after Mars. We literally leap from harmonic node 28 all the way out to Jupiter at node 94. That is a massive gap of 66 K units. The theory suggests this isn't just random empty space, it actually marks a fundamental transition from a low-frequency inter-system resonance out to a high-frequency gas giant resonance. The math says the nodes in between exist, but Jupiter's immense gravitational interference likely stopped any major bodies from forming there.
But hold on. That gap isn't entirely empty, is it? We've got the asteroid belt, and right smack inside that belt is the dwarf planet Ceres. Here is where the framework offers this super fascinating mini-narrative. K7 theory perfectly places Ceres at the 49th harmonic node. That is exactly 7 times 7. So that mathematical point of stability wasn't just abandoned, it was filled by Cirrus. This septenary symmetry just keeps popping up, exactly where the math predicts mass should stabilize.
Now, what's really interesting as we move even further away from the Sun? You'd probably expect a model based entirely on Mercury to start losing accuracy as it stretches billions of miles into deep space, right? Well, the exact opposite happens. When we look at the data for the gas giants, the accuracy levels out there hit up to 99.9%. The paper suggests that out in the deep, far away from the high-energy turbulence of the inner solar system, these massive gas giants have settled almost perfectly into their exact theoretical harmonic points. The wave function just becomes incredibly clean. To truly wrap our heads around the scale of this cosmic blueprint, we really have to compare the leaps between these planets. Remember, the terrestrial gaps are small, just 5 to 10 K units apart. Then we hit that first great jump across the asteroid belt. But the second great jump is truly vast. Leaving Neptune at node 544, we have to travel a staggering 170 K units just to reach Pluto, and whether you want to call it a planet or not, the model places it precisely at node 714. And check out the math again. 714 is exactly 1002 times 7. This huge jump marks the end of the classical planetary system and the absolute beginning of the wild Trans-Neptunian frontier. Which brings us to what is easily the most staggering predictive claim in this entire research paper. It's a single number that radically redefines the boundaries of our celestial neighborhood: 14. The K7 framework essentially posits that our solar system doesn't just consist of 8 planets, or even 9 if you're firmly on Team Pluto. It actually proposes a 14-body orbital resonance model. So the 8 known planets plus Pluto represent only 9 of the 14 major harmonic nodes. That leaves an absolutely astonishing 6 major celestial bodies either undiscovered or maybe awaiting reclassification, just hiding out there in the dark, icy reaches of the Trans-Neptunian region. The mathematical blueprint says the nodes exist, which strongly implies the mass to fill them should exist out there too. So the big question, how do we actually find them? Well, Paul's paper isn't just purely theoretical, it provides a highly actionable methodology. Instead of just pointing telescopes into the dark and, hoping for the best, astronomers can use what the paper calls 1K incremental scanning. The focus should be entirely on stable orbits beyond the 1000K threshold, which is about 55.3 astronomical units away. By systematically checking the specific mathematical coordinates predicted by the formula, researchers can hunt for targeted gravitational anomalies. It takes the search for new planets from a literal blind hunt and turns it into a rigorous process of mathematical verification. The source material actually goes much, much deeper, built on 43 distinct mathematical pillars. Amazingly, the septenary rule scales both up and down. It maps the moons of Jupiter with that exact same harmonic logic. It applies the sequence to other dwarf planets like Eris and Haumea, and it even links the sun's radius all the way back to Mercury's orbit. It literally bridges massive celestial dynamics with the foundational principles of quantum mechanics. It's pretty much a completely unified field view of our local space. Which leaves us with a truly profound realization to take away from this explainer today. Whether you end up viewing K7 theory as just a statistical marvel or a genuine revelation of cosmic mechanics, it completely forces us to look up at the night sky differently. The spacing of the planets isn't some chaotic accident. It's a highly organized mathematical structure. So, if our little solar system follows this precise digital blueprint, what else out there in the massive vastness of the universe is vibrating to the rule of 7? Keep questioning the math that makes up our reality.